I didn't realize, Brice, you are so international, eh? You went all over places.
Yeah, I travel quite a bit.
Excellent. So did you come across with Andy Bunger when you were in Australia?
Yes, I did, because we actually arrived together in Australia.
Oh, is that right?
Yeah.
No wonder you two look like each other. No, just kidding.
Well, I see. So
I'm sure Andy is handsome, but Brice looks better.
yeah. But we will not say the year that we met with Andy. Okay.
Oh, is there?
But it's already a long time ago.
Yes, isn't that? And oh, okay. Andy said, "I'm complimented." Less. But anyway, right now is 10:01. Let's start, Brice. First of all, everyone, thank you for joining this meeting. This is our hydraulic fracturing community Robe talk series. We are blessed. We are truly blessed with all the great speakers, with participants like yourself, accompanying each other in this difficult time. We technically stimulated as well as entertained. And today, over the past week, we have great speakers. You guys all knew very well, from Sid Green, Mark Newbeck, Andy Bunger, Gary Couples, and Mark McCullough. We have this week on Monday, we had Adam Barry from Wales, and today it is our pleasure to have Professor Brice Lecampion to share his research, especially in plannar fracture modeling. Brice is actually quite international, I have to say. This week is our international week. This is not exaggerating. From Wales, on Monday, now we go to Switzerland, and Brice is currently the head of Geo Energy Lab, and at EPFL. I let Brice to pronounce that name later on, but he based in Switzerland. But before joining EPFL, he actually graduated from France, right? And then he joined the CSIRO in Australia. I just realized when we chat, he was at the same time with Professor Andy Bunger. Then in 2006, he joined Schlumberger, become one of the blue guy, move around Europe and the US, and then now he work at the EPFL. There are some house cleaning items I want to state up front, especially for the folks who may not familiar with these Robe talks. New members, welcome aboard. And we normally, this is a Carol technical talk. That means we don't require any release. However, over the past, including today, the presenters actually generously release their presentations and video recordings. So especially for the folks who cannot make it today, you can catch up with this presentation later on. That's number one. So you don't need to take any pictures, any recording yourself. We actually do not encourage that at all. The second, we also do not encourage people forward meeting invite, mainly from legal and copyright point of view. We have to comply with certain policies that set up by either government, US government, and the ARMA organization we belong to. The other thing I want to mention is there are quite a few feedbacks, very good feedbacks from the audience, from participants over the past. One of them, for instance, is asking publications, especially for some of the folks who want to publish. But this year, there are so many meetings, conferences have been canceled. And especially for those fantastic talks, presentations. I mean, those are so mind-blowing and inspiring. If any of the presenters wants to publish a full paper, and we have a venue, we have a channel at the 2020 International Geomechanics Symposium. This year will be held in November in Tehran, Saudi Arabia, if the travel bans are lifted by then. In that symposium, we rolled out an initiative called Publishing Without Registering, which means you don't need to pay the registration, but as long as you submit a paper, there is a deadline. You check my newsletter before all the coming one. I emphasize that as well. As long as you submit the paper, we will peer review and accept or decline, and publish the paper as one of the ARMA publications in one petrol. So those papers will be published as normal ARMA paper. So feel free to send in abstracts or papers to the symposium. As I mentioned, you don't have to register. We encourage you to attend. But as long as you are ARMA member, we provide this service free for all the authors who want to publish in this difficult time. We encourage that, actually. That's why we roll out this initiative. Nevertheless, I will mention more details in the newsletter sent out this Saturday. And we, along with next week's Robe talk. As I mentioned, going forward, we will hold Robe talks once a week on Wednesday. Previously, we held twice a week. And now, as people are going back to office, we reduce the frequency to one talk per week. And we already had a great lineup for the next few weeks. Stay tuned, we're gonna announce them accordingly. Sorry, it took a little bit longer time, Brice, but like I said, today it is truly our blessing and pleasure as well to host. Actually, Brice himself host this Zoom meeting, and he's going to talk about the Plannar monitoring. 45 minutes, 30 minutes presentation, 15 minutes QA. You can type your question in the chat window, and Brice will follow up with either in this chat or as emails afterwards. With that, Brice, feel free to take over. Thank you very much.
Thank you, Gang. Thank you, everyone. So I'm gonna talk today strangely about hydraulic fracturing, you would say, a bit strange for this series, right? And more specifically on the impact of anisotropy on hydraulic fracture growth. So it's a work that has been done mostly by my PhD student Fatima Mukhtari, and also a former postdoc Asib Zia here at EPFL. So at EPFL, I had the Gazna chair on geoenergy, which is a lab where we look at at hydraulic fracturing through induced seismicity, and also hydraulic stimulation for geothermal energy. So today I'm going to focus specifically on planar 3D hydraulic fractures, but investigating the effect of the anisotropy of the rocks, and of course, I mean, as you're well aware, when you walk around, when you look at rocks, especially unconventional rocks, they are always, you know, transversely isotropic. You see the effect of layering is really prominent at different scales. You see here an outcrop of the Eagle Ford along the road. You see also on the bottom left a picture of the Utica at a smaller scale, or on the right here of the Marcellus at another also medium scale. And you see this layering is really prominent, and as a result, the rocks behave as transversely isotropic. And in terms of elasticity, you know, we can write them using the Voigt notation, and instead of two two constants, we have 5 constants. So I'm seeing some people chatting that you don't see my slides, so I don't know why. That's very strange. Okay.
Brice, I can see the first slide, but it seems the slide is not moving. Probably you put on the display on the mode of the president. Yes, it's moving, but right now the slides is in the slide, not in the slideshow mode.
Yes. So if I move to slideshow, okay.
You may have multiple screens.
Yes, okay, I see what I mean. Okay, let me do something. I will stop sharing, and I need to share my screen.
Excellent.
You guys see the slides now? If I change it?
Yeah. Yes, go ahead.
Okay.
Wonderful.
So basically, as you see in this in these pictures, I think we all agree that that the rocks are especially in unconventional transverse isotropy, and most of the works have been done on plane elasticity. So you see in this sketch that you know, most of the case we look at plane strain problems where people have been looking at the deviation or the curving of the fractures due to this transverse isotropy in plane strain. So there's been a lot of work on what I could say dry mechanics on this problem dating back to the 1960s. And also some people have looked at it in the context of hydraulic fracturing. I'm not going to talk about that case today, as you will see. Why is because in most situations, the situation that is of interest on the practical side is really 3-dimensional. So I will switch to the next slide and look at the case really of I don't know why my slides are behaving strangely, of an horizontal well where we have an hydraulic fracture, so a horizontal well drilled in the direction of the minimum stress, and where we have horizontal layering. And this horizontal layering is the material isotropy plane. Now, in a lot of cases, in unconventional reservoir, we have either a normal or sometimes track-slip stress regime. There is some, of course, some cases where we might have a reverse stress regime, but I would say the normite and strike-slip stress regime are the most current ones. So in that regime, the fractures grow in a plane perpendicular to the material isotropy plane. So the fracture grow vertical, and the material isotropy plane is the horizontal plane. Okay? And so we are in this situation where the fracture has a 3-dimensional nature. It's going to be probably more elongated in some direction, and it's vertical, perpendicular to the isotropy plane. So in that limit, we can look again at a model of a planar three-dimensional fractures. And this limit, you can investigate it in the case where there is no deviation of the hydraulic fractures in the bedding plane, okay? So the fracture will always be propagating perpendicular to the bedding planes. So for that to happen, you imagine that it's gonna, the bedding planes are usually weaker, right? So the hydraulic fracture may want to deviate in those planes. But here we're looking at a case where the vertical stress is sufficiently large to prevent that from happening. So at a continuum level, we will have a planar hydraulic fracture propagating perpendicular to the material isotropy plane. So what do we want to talk about? I don't know why my slides automatically switch to the next after 2 seconds. It's a bit strange. So we want to look at the case where the uniform, the in situ stress field is uniform, okay? So no stress jump, okay? And we want to investigate the following. How the transverse anisotropy of the rock control the deviation from a simple radial hydraulic fracture geometry, because we know that if we are isotropic and we have just a point injection, the fracture will be a radial shape. But how does the anisotropy change that picture? The first thing, okay? What is the shape of these fractures? And then, what is the effect of the anisotropy in the competition between viscosity dominated propagation, where most of the energy dissipated is into fluid flow in the fractures, and toughness propagation, okay, where the energy spent is in really breaking the rock. So for simplicity, in the following, the rock is impermeable, so I will assume there is no leak off, and the rock is also homogeneous. So we basically, all the layering is treated as a continuum, as a transverse isotropic rock, okay? So the thing is that fracture mechanics become slightly more complicated in transversely isotropic, in the elastic transverse isotropic case. Slightly is an understatement. It's quite more complicated. So our stiffness sensor now has five parameters, and the expression are more involved, all right? But you can still show, okay, that in that configuration of a planar fractures, the fracturing mode decouples. So what does that mean? That means that the hydraulic fracture being normal to the minimum in situ stress, there is no shear acting on that planar hydraulic fractures, and basically the opening mode doesn't induce any shear stress on the plane of the fracture. Okay, so we are pure opening mode. Okay, the shear on normal mode decouples like in isotropy, but in the case of transversely isotropic media. So the elastic equation that we have, you know, we can write the equilibrium equation and get a boundary integral representation linking the traction on the fracture surface, T, to the displacement jump. And it has a form which is similar to the isotropic case, except that this kernel SK2M here is just very nasty, and it will not even fit into a slide. Okay, but it exists, and there is solution for it, and we can leverage the same techniques than for isotropy. So now just recalling very fast the formulation of the problem for the case of an hydraulic fracture propagation. We have an elastic boundary integral equation, the one that I mentioned before, where now the traction on the fracture surface are the fluid pressure minus the in situ compressive stress, the minimum horizontal stress. So this is the net pressure, which is related to D, which is the fracture opening, okay, in our notation. After, we have the classical assumption in the case of an impermeable medium of lubrication flow, okay, with Poiseuilleot. And then we have a propagation condition, and I will come back to that in a minute, in the case of anisotropy. I will talk about sufficiently deep fractures so that the fracture front and the fluid front coalesce, okay? It's the case of zero fluid lag, which is achieved at practical depths very quickly. So this type of class of problems, we know that they are really affected about what is happening near the fracture tip, okay? And that the competing process of viscous dissipation on breakage of the rock really clash at the fracture tips. So you can, for a radial hydraulic fracture here, you can zoom close to the front. If you are sufficiently close to the front, you can view locally the problem as semi-infinite fractures propagating in plane strain. Okay, so that's important to understand. And after, there's been a class, you know, a solution of that problem, coupling elasticity and fluid flow, that has been obtained and actually verified experimentally. So in this plot, I just recall it. This is experiments actually from Andy, where basically he measured in transparent material the width of the fracture with the distance to the tip, and also measured the velocity of the fracture, and he remapped it into this semi-infinite fracture solution, where you see that you have a transition between kind of two regimes, a regime where the fracture toughness dominates, where we have the square root behavior of linear elastic fracture mechanics, and a far field behavior, which is governed by viscous flow, a two-thirds asymptote. So that's for isotropy, okay? So the point is, when we move to anisotropy, what is going to happen? So let's go back and first look at the configuration, okay? So I will go over the sketch. So we have the fracture, which is here. And if we move and walk around the fracture front, the propagation direction, if locally we put ourselves at point A, we can still zoom and view locally the fracture as semi-infinite and plane strain, propagating in the so-called divider direction, okay? And whereas if we put ourselves at point C, we see again a plane strain situation, plane strain configuration, but this one, the hydraulic fracture is propagating in the arrestor direction perpendicular to the layering, okay? And in between, at point B, well, you know what? The fracture front, the tangent to the fracture front, is at an angle with the material isotropy plane. So it's like an intermediate configuration. So that's important because if we recall fracture mechanics, there is a relation between stress intensity factors at the tip and the energy release rate, okay? This is the so-called Irwin relation, which is a plane for a coplanar fracture growth. And that's related, so G, the energy release rate, to K, the stress intensity factor. In anisotropy, in the general case, you've got this expression, which is chi I times the matrix lambda ij kj, where you can have a coupling between modes, right? In our configuration, there is it's simplified a little bit. And we have mode decoupling. So we have a relation which is similar to Irwin, K1 squared divided by E prime for the relation between energy release rate and stress intensity factor. But now the E prime is depending on alpha. Alpha is this angle made between the normal to the front and the material axis locally. So we can, because we are in pure mode 1, still rewrite the propagation condition as local stress intensity factor equal to K1C. But now the stress intensity factor will vary along the front, and also as the material properties, the fracture toughness may also vary between a fracture propagating in the divider direction or the arrestor direction. So after, you can do some maths and get this expression of E prime alpha. I will not go into the details, but basically by a change of coordinate system and knowing the solution for dislocation in orthotropic media, you can get the expression of E prime alpha, and you can show that actually the elastic operator for this plane strain configuration are exactly the same form than the isotropic one, pending the use of this E prime of alpha. So E prime of alpha, it has a nasty expression. I put it here, but it's analytical. You can get it analytical, and you also have expression, for limiting conditions. So we get back, known expression in the case of alpha equals 0 in the divider direction or in the arrestor direction. So this is analytical. So you can, it's function of what? It's important to discuss this. It's function of beta, which is going to be the ratio of the modulus in the divider versus the arrestor direction. So this is like the intensity of anisotropy, and also some Thomson parameter, which characterize the anisotropy of the rock, and the ratio with C13 over C11. I'm just going to show you briefly how this evolves. And the major effect is, of course, beta. So here on the x-axis, you've got alpha, this angle, this propagation direction with respect to the material axis. And in the vertical direction, you've got E prime alpha scaled by the average. Okay. So the effect of beta is larger. So if you increase beta, well, the difference between alpha equals 0 and alpha equals pi over 2 are increasing. And also you see some change in the intermediate region. The other parameters have a weaker effect, but they still affect the intermediate region. They don't affect the value at 0 and pi over 2, but they affect the transition. Okay. Some expression for this E prime alpha, some approximated expression have been proposed in the literature. So I've put it here in dashed line, and you can see that it can become. So the approximation is correct again at alpha equals 0, alpha equals pi over 2, but in the intermediate range, it's quite off as soon as you've got beta larger than 1.2. So it's important to account this full effect of variation. So some example of some rocks. We took several rocks just to give you an order of magnitude of the type of change. And the most important one that I want you to really pay attention to is beta. This is the one that has the first order on that I will discuss mostly. And it basically for normal rocks, it can vary, from Micagness 1.15 and very, very anisotropic, the most anisotropic we could find, close to 2. Okay, so the range of variation is between, let's say, 1 and 1.6 for most of the rocks. Okay, so that's for elasticity. So now, what about fracture toughness? Sorry, I have a problem with my slides that automatically shift. So the fracture toughness, anisotropy, there is very few lab data, okay? Most of the laboratory data, you can find some data in the divider direction, in the arrestor direction, but as function of this angle alpha, there is very little actually. Most of the tests are done in the other configuration, between the E2 and E3, and not in this E1, E3 plane. Nevertheless, there is few publications where there is some values, and it seems that between the divider and the arrestor direction, the toughness can vary between maybe 1.1 to 1.6. Okay, so again, a range which is not an order of magnitude, but you can have a variation between these two. Of course, the toughness in the bedding plane is usually much weaker than this. So after that, that's let's say the toughness in the two direction, and then you have to have a law for the evolution of the toughness as function of this propagation direction alpha. So a simple law that you can use if you don't know anything is to use this cos square sin square as a smooth transition between the two, right? That's a possibility. Then actually in the literature, there is some solution for elliptical fractures, because elliptical is simple enough to solve, right? And in the case of an elliptical fracture, you can get an expression of K1, the stress intensity factor, if the fracture is loaded with a uniform stress, as function of this alpha or an angle theta, which is related to alpha. So we can also use this law, and it's actually useful, because if we use this so-called elliptical anisotropy, we should in principle get an elliptical shape of the fracture. So it's a good check for the numerics. So what I'm gonna present after is mostly numerical results, and we have redeveloped a Plannar 3D hydraulic fracture simulator, and including transversely isotropy, okay? So this simulator is based on the implicit level set. I will not go through it. I'm just gonna highlight the fact that these schemes use the tip asymptotes near the fracture front. So the key point is that these hydraulic fracture tip asymptotes, when we use them, we allow us to have a slightly coarser discretization, and they also are extremely accurate. Okay, so the schemes iterate as the fracture front as a level set through the Cartesian grid, and the elements that are cut by the fracture front, the tip asymptotics are imposed, and they are coupled with the cell inside the fracture, where this ribbon cell, which are the cell here in magenta, are used to basically couple the tip with the center of the fracture, the channel. Okay. So I will just skip that and just make the point of what is the change in the case of transverse isotropy. Okay. In the case of transverse isotropy, first of all, you need to have a displacement discontinuity method, which handle, of course, the transverse isotropy of the rock. So that exists, and some element for transverse isotropy exist in the literature. So we use those. And then after, as I've mentioned before, we can use the plane strength configuration is the same than in the isotropic case if you use the proper modulus, which is function of the propagation direction. Meaning that when we do invert the tip asymptotics in the scheme, we don't know a priori the propagation direction, so we have to iterate for it. So we invert the tip asymptotics for a given trial propagation direction, which is the one of the previous time step. We propagate the fracture front, and we get a new, we check again the propagation direction at all the survey cells, And we repeat that until we converge, okay? So basically, it's a bit more heavy than in the case of isotropy. So first of all, verification. The elliptic crack in a toughness-dominated regime, there is a solution that can be derived, okay? So this solution is analytical. It's, again, only valid if you impose a peculiar form for the evolution of the fracture toughness with the propagation direction, with this angle alpha, okay? So if you impose this peculiar constitutive relation for the fracture toughness, you should get exactly an elliptical fracture, and its growth is self-similar in the toughness case. So we can use this to benchmark the code, and we did, and it's working very well. Though we get exactly the values of the minor and major axis, and their evolution with time is with the power law, which is exactly the same than in the isotropic case. The propagation is self-similar for an ellipse, and we have a difference between our numerics and the analytical solution of, as you can see, less than 2%. Interestingly, there is also a scaling for the aspect ratio. So the aspect ratio of the ellipse is function of the ratio of the toughness in the two direction and the moduli in the two direction, 2 power 2. So you can have, even though you have slight anisotropy of moduli and slight anisotropy of toughness, if they are compounded and they are to the power 2, you get a very elongated fracture, okay? After, if we go to, for the general case, I will just recall that in the case of an impermeable medium, if the material is isotropic, you know the hydraulic fracture solution is a radial shape, and it evolves from an early time solution dominated by viscosity to a late time solution dominated by fracture energy, toughness. There is scaling in these two regimes. There is actually even solution in these two regimes. And there is a transition time scale, TMK, which gives you the time it takes to transition from one regime to the other one. In the case of transverse isotropy, now the fracture is not properly radial. So we are looking for the shape of the fracture. We can scale it with a characteristic line scale, and we know it's going to be function of the elastic anisotropic parameter. So Thompson parameters is beta, C13 or C11, the ratio of toughness, and also the evolution between viscosity and toughness dominated regime. So this time scale of transition between the two regimes, that depend on E prime and K prime. So we can define one for the arrestor for the divider direction and one for the arrestor direction, so vertical and horizontal, okay? And the ratio of the two time scale in these two directions is related to the ratio of the moduli to the power 13/2, ratio of toughness power 9. So again, you can see that only a slight anisotropy can introduce a very large effect on the propagation of the fracture, because you can have a ratio of the two time scale that are, you know, in the 500 easily. So, okay, so I will now look at the results and try to separate the effect. First, I'll look at isotropic elasticity and anisotropic toughness. I will go very briefly on that. Then switch to transverse isotropy and make the case of isotropic toughness. Okay, so this other extreme. Look at viscosity toughness dominated, and I will just at the end put the two together. So fracture toughness and isotropy only, you see that there is at the beginning, because there is no elastic anisotropy, the fracture is radial. Okay, so the two semi-axes are equal. And then after a while, you have a transition toward toughness dominated, where you have a transition which is faster in one direction than the other. which is related, which is this difference of time scale between one of the or the other, which is 500 in that case for a ratio of toughness of 2. So I showed in that picture some snapshot of the propagation where the times start. So at the bottom, early time, at the top, late time, where at the beginning you see that the propagation is radial. And as we move towards the toughness dominated propagation, the fracture starts to feel the toughness anisotropy and gets elongated. And at the end, we've got a large elongation. Okay. So the take-home message here that you can have really large amplification from the effect of the anisotropy for toughness. In that case, it's power 2. Now, if I switch to putting elastic anisotropy and look at the early time, so viscosity dominated, we get the same type of power law behavior that in the isotropic case. The fracture gets slightly elongated, but you see that in this log-log plot, you don't even see it. So the effect is not large, okay? So you could look at it in terms of the fracture footprint. So here it's the fracture footprint, which are self-similar, okay, because the fracture propagates in a self-similar fashion. So the shape is always the same, it's just a rescaling of the space in time. And you see that as beta increase, indeed, I mean, the fracture deviates from the radial shape. This is a quarter of the fracture. The isotropy is this quarter circle here. And as beta increase, you have a slight deviation and the fracture gets a bit elongated. But it's not large, okay? And the scaling of the elongation, so if you take the semi-axis and the major axis, B over A, it evolves as beta to the power -1/3, and you can recall that scaling from the tip asymptotics actually. So now, if you go later in time and you look at the toughness dominated case, then the fractures also propagate in a self-similar fashion, similarly to the isotropic solution. But now you see that the difference between the minor axis and the major axis are much larger, okay? So now we start to see the effect. This is the case of an isotropic toughness, only anisotropic elasticity. So if you look at the self-similar shape, they are much more elongated. And as you increase beta, which is the primary factor, you get relatively large elongation. The effect of the other parameter, C13 over C11, epsilon and delta, are really second order, as you can see. They don't affect the shape very much. The scaling here is beta to the -1, -2. So the effect of beta is large on this elongation. I will not go into the fracture shape. I will just now say a few points. So viscosity dominated regime early time, the effect is relatively small on the footprint, which stays relatively radial. There is a small effect on an effect on the width and the pressure. There is a very strong effect in the toughness dominated regime. I didn't mention, but the fractures are not really elliptical because the toughness is isotropic, but they are close to. They are maybe 10% of an ellipse. The effect of beta, the ratio of moduli is order 1, and the aspect ratio evolves as beta -1/2. And another point is that the transition between viscous and toughness is, to a power 13 over 2, so to a very large power. So you have a very different time scale of transition in the vertical and horizontal direction. You can play around, you can look at the case where you have isotropic fracture energy. So now it's not isotropic toughness, it's isotropic fracture energy. In that case, the elongation scale with beta to the power -1. Okay, this is directly related to Irwin relation between stress intensity factor and energy release rate. So the conclusions are the same. It's just what changed is that now the scaling is as function of beta for the elongation, and the time scale are 2 to the power 2 and not 2 to the power 13/2. Finally, you can also look at viscosity to toughness regime. I just saw 2 simulations just to tell you that the ratio of time scale that I've discussed before, which scales in, so this ratio of moduli to the power 32/2 and toughness to power 9, also hold, okay? And that you have, you know, in the case either isotropic toughness or fracture energy, you can see a transition from the M regime viscosity where the fracture is nearly radial to a case where at the end the fracture are nearly elliptical. But you can ask yourself, okay, what about the case where the toughness varies, is not isotropic, and GC is not isotropic? Maybe there is a variation. So I mentioned this cosine sine law for the toughness. So we did simulation with it, and we compare with the approximation of an isotropic toughness, which is in black, or the approximation of this peculiar form of evolution, which gives a strictly elliptical fracture. And you see that for the same ratio of toughness and the same ratio of elastic isotropy, you end up having different elongation. Which poses the question that, okay, what is the proper law for the evolution of fracture toughness as function of propagation direction? And the response is, of course, in experiments. This is the only thing, you know, we can rely on robustly. So I will conclude here by a few points. Sorry, stopping my slide, going crazy. So first of all, transverse isotropy is always there. And I think we need some time to take into account. I think in a lot of time, it's important. Even in the absence of in situ stress contrast, as you have seen in homogeneous case, there is an effect of this elastic and toughness anisotropy, and that can result in significantly smaller height growth of the fracture. The fracture gets elongated and propagate more in the horizontal direction. Of course, this is maximized in the toughness dominated regime, okay? But another important point is that the transition time scale between viscosity and toughness is widely changed and vary between the vertical and horizontal direction. So in practice, the toughness regime will be reached fast in the vertical direction, and that will promote containment of the fracture. Another point I mentioned in the last slide is the exact form of the evolution of the fracture toughness or the fracture energy as function of the propagation direction, not only the value in the two, you know, in the material frame, plays a critical role on the final shape of the fracture. And also they are not elongated, the fracture, so also they are elongated, these fractures, they are not exactly elliptical. They are elliptical only for a very peculiar form of this evolution of toughness. So as perspective, few of them. First, we need measurements of anisotropy of fracture energy as function of the propagation direction. And in my opinion, they are lacking. There is some along the material axis, but we need also propagation direction in other direction, in direction for different alpha. Also, after, what we want to do here at TPFL is to actually do experiments of hydraulic fracture propagation in this type of rock test, some of the findings that I've discussed today. And we have done so. We have preliminary results. I'm not showing them yet because they are very preliminary. We see two things in the experiments. First, that we need very large deviatory stress to ensure that the fracture really stays perpendicular to the bedding plane and don't deviate in the bedding plane at the scale of the lab, right? But we are able to do some experiments, and I put a picture here, and you see basically the created fracture plane of a fracture which propagates perpendicular to the bedding plane, to the isotropy plane. And you can see the isotropy plane, which are vertical here in that picture, and the fracture roughness, which is clearly anisotropic as a result of this layering of the material, which pops up maybe something that we don't have in our model yet, is the fact that this fracture being so rough and the anisotropy of roughness is so prominent that possibly in the lubrication flow, we have a kind of an anisotropic viscous drop. And that may result in stronger elongation even in the viscous dominated regime. This is a postulate. We need to do more experiments and to actually measure the fracture front when it's propagating. It's a work ongoing. After also a point, I mentioned that we really need to have large stress normal to bedding to prevent jogs. Of course, it's not always going to be the case in reality, and it's clear that when SV is smaller, that will promote jogs. Okay, so at a small scale, we will have the fracture wanting to go into some beddings, maybe deviating again after to the vertical direction, etc. And that will surely, of course, promote vertical containment. Now, the big question from a modeling point of view is, can we define from this jogging an equivalent anisotropic macroscopic toughness that we could use in a continuum model like the one I've discussed today? So with that, I will stop. I hope that my problem with my slides overtaking my marks didn't cause you too much trouble. So I'm happy to take questions.
Thanks, Brice. Before we have a few minutes for the questions. I see people typing questions into the chat window already. Brice, feel free to take on those questions. But first, thanks, Brice. This is very nice settings, eh? No wonder you want to go to your office.
Exactly. Well, this is taken on a sunny day.
Nice. And before anything else, thanks, Brice, again for sharing these insights. For the folks, many folks probably, the audience understand probably a mix of academia and the industries. For the industry folks like myself, don't be deterred by the equations. That's exactly why we held many meetings over the past, especially from hydraulic fracturing community, to bridge the academia and the theory developers with industries, so that we can connect the two sides better. So that's actually why you are in this meeting. Having said that, I just want to announce the next week talk before I hand over to Brice for his questions. The next week, Tom Doe from Golder. Tom Doe was a previous ARMA past president, and he semi-retired from Golder, but he is kindly offering a topic which everyone likes, okay, regardless of academia or industry folks, is stress measurement, okay, hydraulic fracturing stress measurement protocols. Okay, we're talking about the fundamentals of stress measurements, and he will actually discuss from both civil mining two industries with petroleum applications. So the three industries come together, talk about the stress measurement. So don't miss next Wednesday. And Brice, feel free to take over. As I mentioned, the Zoom meeting ends probably at 11, but feel free to stay longer if you guys have further questions. Brice, thank you very much. And those guys waiting for the slides, Brice will release, and I will announce them in the newsletter. If you are not receiving my newsletter over the past, so that means you need to send me email to get on that email list, to receive the link, to download the presentation. Brice, feel free to take over. Thank you very much, Brice.
Yeah, thank you again. I will send you the slide later this evening. And so yeah, just before going on, I mean the work, the details of all this work, you can find it in some papers that have been recently published. So I will, the links will be in the slides. So to answer the first question was about the weak anisotropy. Okay. Our theoretical solution actually are for full anisotropy. That's really what we wanted to do, because indeed some people before did some approximation for some kind of weak variation of anisotropy, and so we really take into account the effect of the full impact of the anisotropy. So maybe I can show you again the slides where we have this. This is embedded really in this evolution of this E prime of alpha, which is characterizing at the scale for that particular problem of this anisotropy. And you see, so the solution with a full anisotropy is a continuous black line here, and the approximation for weak anisotropy is this dashed line. So it's the same in the two directions of the material axis, but it's widely different in between. And so that has an important impact indeed. After Colin, I see you did a question related to the ratio of sigma V or sigma H, right? This is indeed very important, and I've tried to relate it to a little bit in the end. So in the case of a planar fractures, perpendicular to bedding, the fracture is never going to the bedding plane in the model I presented today. Also, you can view it as a macroscopic model, so you could relax the fact that you need a very large sigma V, and that you may have jogging at bedding planes, but that at a macro scale, the fracture is more or less still planar. Now, as far as the limit, where we could see a transition from this fracture, which is planar, perpendicular to the bedding plane, and let's say a T-shaped fracture, where at some point at one bedding plane, it just go perpendicular to it. I cannot answer your question. We don't have, I think, an exact criteria for this at the moment. Romain, you asked about this measurement of toughness, right? This first perspective. So we try to do it. We try to do it, and it's very difficult. Indeed, you can. It's easy to measure the toughness along the material axis, so whether in the divider or in the arrestor direction. In between, it's very difficult. We got few measurements, but it's difficult. So you can do what we ended up doing is a semicircular bending test, which are easy enough to prepare the sample. There's probably some other configuration that we need to be investigated. But yeah, this is something we are trying to pursue. And if also some other people have ideas about this, I think that would be very worthwhile to try to understand more the effect of the variation. After, our hope as well is in our experimental setup is we use acoustic waves, so ultrasonic active acoustics, so doing like a 4D ultrasonic survey in the lab during the propagation, and we hope that we will be able to measure the fracture front evolution with time. And if we see elongation, we possibly can relate and have some clues about this evolution of fracture toughness if we do an experiment in the toughness dominated region. So feel free to ask questions if you have. Also, a note for the one that are interested. The code that was used for the simulation is open source because of the research was funded by the Swiss National Agency, and you can download it from our webpage at TPF. And it has this anisotropic effect in it. Now we did mostly the simulation with realistic values of anisotropy, right? Which span the one of the rocks that we have found in the literature. And the code seems to work in that configuration. Then we put also, we try to go to very, very large anisotropy to see, you know, if we still work. And it's of course more difficult as the anisotropy gets amplified, because the curvature of the fractures is getting very, very sharp in one direction, and that's difficult numerically.
All right, Brice, I hate to cut you off, but
Yep.
For this particular Zoom meeting, I think we reached the time,
Yep.
11 o'clock. However, Brice is the host of this meeting. For the folks who want to stay longer with him, feel free to do so, providing Brice is available. But for the rest of folks, our meeting technically stopped, but we will see you next Wednesday at the Tom Doe's stress measurement from civil, mining, and the petroleum industry. Anyway, Brice, thank you very much again, and stay safe and well, and that's most important. While you crack all the equations is the second. Let's stay in touch, and thank you again for sharing this great work, great efforts. And for the rest of you, I'll see you next week.
Thank you again. Thank you a lot for organizing this.
Sure.
And I can answer also some. I've seen one other question because I didn't see that there were Q&A and chat, so people are asking questions in the two. There was one question about bedding plane and possible shear slip at the bedding plane. So for now, the model that we have doesn't account shear slip at the bedding plane. Okay, so that has, of course, an important effect, and especially if you look at after deviation into the bedding plane and this jogging effect, or our model is at the continuum scale, so we assume that the fracture is planar and there is no shear on the bedding plane. But these small jogs, they could somehow be maybe upscale into an anisotropic toughness. But that's, you know, how to do that is still a bit unclear in my mind. There is another question about the analytical solution consistent with the numerical solution. So the analytical solution actually have the same assumption, but they are for limiting cases. They are in the limiting case where there is no viscosity. So they correspond to the so-called toughness dominated regime. So that's a limiting case, and we use them to benchmark, especially that the numerics is properly capturing the elongation of the fracture, the fact that the fracture is not radial anymore. Can you manufacture anisotropic toughness material? That's a very interesting question. We thought about also trying to use a synthetic material, and I tried to look, and I didn't found a good solution. We tried several things. I had a student trying to glue, layers of glass, but that was not really a huge success. And the best we could find was a slate from Spain, actually, that we are testing. That is finely laminated it's late. So is toughness between the arrestor and divider direction still K1C? So if the fracture is planar, the mode still decoupled, so you can be in pure mode 1. So if you're able to propagate in that direction a plane strain fracture, so with a straight front, you would be able to get a parameter which is acting to a K1C for this particular direction. But it's very difficult when you are not in 0 or pi over 2 to have a front, to propagate a fracture which is as a straight front. As effect of microscopic roughness, that's for sure. And you can see it on this picture, even though there is no jogs. Well, you can say actually there is jogs, because all this little roughness that you see created are the results of these like small jogs in between the fine layers. And that is something that's still, not really quantify as how much this anisotropy of roughness that you see created on this fracture actually influence the problem. But that will, I think, in my opinion, even reinforce the effect that the fracture gets even more elongated. So if there's no other question, I will close the meeting. So as Gang say, I will send him the slides, and the recording also will be available. And you can always send me some emails if you have additional question or want some additional information about this work.